Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into a crucial aspect of process management: process scheduling. Sheila, why don't you kick us off with a quick overview of what process scheduling is all about?
Absolutely, Victor. Process scheduling is essentially how operating systems decide which process gets to use the CPU at any given time. It's a key part of multitasking systems, allowing multiple processes to share the CPU efficiently. Think of it like a busy restaurant kitchen where the head chef has to decide which dish to work on next to keep all the customers happy.
That's a great analogy, Sheila. Now, before we dive deeper, let's talk about something called the CPU I/O burst cycle. This concept is key to understanding why we need process scheduling in the first place.
Sure thing. The CPU I/O burst cycle describes the pattern that processes typically follow. A process starts with a CPU burst, where it's actively using the processor, followed by an I/O burst, where it's waiting for some input or output operation to complete. This cycle repeats until the process finishes.
Exactly. And it's this back-and-forth pattern that makes process scheduling so important. While one process is waiting for I/O, another can use the CPU, maximizing efficiency. Now let's talk about the star of our show today, the CPU scheduler.
The CPU scheduler is like the head chef in our restaurant analogy. It's the part of the operating system that decides which process in the ready queue should be given CPU time next. This decision is based on a scheduling algorithm, which we'll cover in more detail in a future episode.
Great explanation, Sheila. Now, let's dive into a key distinction in scheduling: preemptive versus non-preemptive scheduling. This is a concept that often comes up in interviews, so listeners, pay close attention.
Absolutely, Victor. In non-preemptive scheduling, once a process starts running, it continues until it either completes or voluntarily releases the CPU, typically when it needs to perform an I/O operation. It's like letting a chef finish preparing an entire dish before moving on to the next one.
Exactly. And in contrast, preemptive scheduling allows the operating system to interrupt a running process and move it back to the ready queue. This might happen when a higher priority process becomes ready to run, or when the current process has used up its allotted time slice.
That's right, Victor. Preemptive scheduling is more common in modern operating systems because it allows for better responsiveness and fairness. Imagine if your smartphone couldn't interrupt a background app to respond to your touch input. That would make for a pretty frustrating user experience.
Great point, Sheila. Speaking of smartphones, they're a perfect example of why efficient process scheduling is so crucial in modern computing. With dozens of apps potentially running at once, smart scheduling decisions are essential for maintaining performance and battery life.
Absolutely. Now let's talk about another important component of the scheduling process, the dispatcher. Victor, can you explain what the dispatcher does?
Certainly. The dispatcher is the module that gives control of the CPU to the process selected by the CPU scheduler. It's responsible for three main tasks. First, it switches context from one process to another. Second, it switches to user mode. And third, it jumps to the proper location in the user program to resume that program. The time it takes for the dispatcher to stop one process and start another is known as the dispatch latency or context switch time.
That's a crucial point, Victor. Context switching is a necessary overhead in multitasking systems, but it's important to keep it as efficient as possible. Every time a context switch occurs, the system has to save the state of the old process and load the saved state of the new process.
Exactly right, Sheila. And that's why modern operating systems and processors have various optimizations to minimize context switch time. For example, some processors have multiple sets of registers to quickly switch between processes without having to save and restore register contents to memory.
That's fascinating, Victor. It really shows how every aspect of computer design, from the hardware to the operating system, works together to maximize efficiency. Now, as we wrap up, let's quickly recap the key points we've covered about process scheduling.
Great idea, Sheila. Here's a summary for our listeners. 1. Process scheduling decides which process uses the CPU at any given time. 2. The CPU I/O burst cycle describes the alternating pattern of CPU use and I/O waiting that processes typically follow. 3. The CPU scheduler selects which process in the ready queue gets CPU time next. 4. Preemptive scheduling allows the OS to interrupt running processes, while non-preemptive scheduling doesn't. 5. The dispatcher is responsible for actually switching control to the selected process. 6. Context switching is a necessary overhead, but efforts are made to minimize its impact.
Excellent summary, Victor. And remember, listeners, understanding these concepts is crucial not just for operating system design, but also for writing efficient, responsive applications. Whether you're preparing for an interview or just want to understand your devices better, this knowledge is invaluable.
Absolutely, Sheila. That wraps up our discussion on process scheduling. Thanks for tuning in, everyone. In our next episode, we'll be diving into operations on processes. Until then, keep your processes running smoothly.